The universe may be playing by different rules than we thought. The fundamental constants of physics, numbers like the speed of light, might not be constant at all. Albert Einstein once marveled that the universe is comprehensible, but what if our understanding is built on a foundation that is slowly shifting? This is not science fiction. It is a serious frontier of modern science. By the end of this journey, you will see the cosmos through a completely new lens, questioning the very nature of reality itself. We will investigate ancient starlight that carries secrets of a different past and examine a 2-billion-year-old nuclear reactor buried deep underground. What clues would convince you that the rules of reality are not written in stone? These fundamental constants are the universe's deepest operating code. They are not just numbers in a textbook. They are the numerical values that appear within the very laws of physics themselves. Think of the speed of light, often called c, a universal speed limit that nothing can exceed. Or Planck's constant, h, which governs the bizarre and tiny quantum realm. Then there is the gravitational constant, g, which dictates the strength of gravity's pull across the cosmos. These are not mere measurements, they are the fixed parameters, the unchanging settings that dictate how everything interacts. They control how particles collide, how stars fuse hydrogen into helium, and how the entire universe has expanded from its first moment. Imagine our reality as an incredibly complex simulation. The fundamental constants are the code written into that simulation, the numbers a programmer set at the very beginning that determine all the rules. Their values are bizarrely precise. If the fine structure constant, which governs the strength of electromagnetic interactions, were even slightly different, the consequences would be catastrophic. Stars might not burn properly, or the crucial element carbon might never form inside them. Without carbon, the chemistry of life becomes impossible. Our existence hinges on these numbers being exactly what they are. This precise cosmic recipe provides the stability that makes science possible. It allows us to predict eclipses thousands of years in advance and to build technologies like GPS that rely on the unwavering nature of these rules. But this foundation of stability is precisely what is now under a microscope. What if this perceived constancy is just a temporary phase, a local phenomenon in a cosmos that is far grander and more dynamic than we ever suspected? The mere possibility that these bedrock numbers could change forces us to question everything we think we know about reality, launching our investigation into the evidence. This bedrock assumption of an unchanging cosmos was the very engine of scientific progress. Isaac Newton envisioned a universe of absolute space and time, a perfect stage where his laws of motion and gravity played out with unwavering consistency. In this clockwork reality, the gravitational constant was simply a fixed number in an equation, a fundamental feature of the universe that was the same yesterday, today, and forever. This framework was breathtakingly powerful. It allowed us to predict the orbits of planets with stunning accuracy and to understand the forces that bind our world together. Later, James Clerk Maxwell's elegant equations for electromagnetism did more than just unify electricity and magnetism. They revealed the speed of light not as a mere measurement, but as a fundamental constant derived directly from the laws of the universe itself. This was a profound confirmation. The constants were not just numbers we measured, they were the immutable pillars upon which reality was constructed. The entire scientific method is built upon this foundation of constancy. An experiment performed in London must yield the same result when performed in Tokyo, or on Mars, or in a distant galaxy a billion years from now. Without that guarantee, science as we know it would be impossible. Our greatest technological triumphs, from the electrical grid to the Apollo moon landings, are testaments to our trust in this cosmic stability. We built our modern world on the faith that the rules of physics would not change overnight. Yet, this very success created a kind of intellectual inertia. The idea that these constants could change was not just heretical, it seemed entirely unnecessary. Why would anyone question the solidity of the ground beneath their feet? But every paradigm, no matter how successful, eventually meets an anomaly it cannot explain. The first crack in this foundation of certainty would appear not in a laboratory on Earth, but in the faint, ancient light of distant quasars. The first whisper of a changing reality came not from a telescope, but from a theoretical physicist staring at a set of numbers. Paul Dirac, a towering figure in quantum mechanics, noticed something deeply puzzling in the 1930s. He observed that the ratio of the strength of the electromagnetic force to the gravitational force is an immense number, roughly 10 to the 39th power. That is a 1 followed by 39 zeros, and then he looked at the age of the universe expressed in certain fundamental units of time, and it was also a number around 10 to the 39th power. To most scientists, this would be written off as a simple oddity, a numerical coincidence with no deeper meaning, but for Dirac it was a signal. He proposed his large number hypothesis, suggesting this was not a coincidence at all, but a profound clue. The gravitational constant, big G, the very strength of gravity, might be slowly weakening as the cosmos grows older. This was a breathtakingly radical idea. It meant that the fabric of reality was not just expanding, but its fundamental rules were actively evolving. The force that holds planets in their orbits and governs the collapse of stars could be different now than it was in the distant past. For a scientific community built on the bedrock of constants, this was a deeply unsettling proposition. Yet the seed had been planted. A few decades later, in the 1960s, theorists like Robert Dicke and Karl Brands took this idea and built a new framework for gravity itself. Their scalar tensor theories were extensions of Einstein's general relativity, but with a crucial twist. In these models, constants like the gravitational constant were not fixed numbers. They were dynamic fields capable of changing their value across space and throughout time. These theories were not immediately accepted, and they remained on the fringes of mainstream physics. But their importance was monumental. They transformed our conception of physical law from a set of rigid, immutable rules to something that could be part of the cosmic drama itself. The laws were no longer just the stage on which the universe played out, they were actors in the play. This theoretical groundwork was essential. It gave scientists the mathematical and conceptual permission to ask a question that was once considered heretical. What if the numbers in our physics textbooks are not universal truths, but are merely local readings, a snapshot of the rules as they are here and now? With this door now open, the search for evidence could begin in earnest, leading us to look at the oldest light in the universe for answers. Edwin Hubble's discovery that the universe is expanding did more than just reveal galaxies flying apart. It introduced the concept of deep time into physics. The cosmos has a history, a narrative stretching from an unimaginably hot and dense beginning to the vast, cool expanse we see today. If the stage itself is evolving, could the very rules of the performance be changing as well? The expansion is governed by its own set of constants, but this grand perspective turns the entire visible universe into a natural laboratory for testing their permanence. In its first fleeting moments, the universe was a seething cauldron of energy where the fundamental forces we know today, gravity, electromagnetism, and the nuclear forces, were likely fused into a single, unified interaction. Think of it like a hot gas where all the molecules are moving freely and rapidly. As this primordial cosmos expanded and cooled, it underwent a series of cosmic phase transitions, much like steam condensing into water and then freezing into ice. At each critical temperature, a force broke away, freezing out into the distinct entities we now measure in our laboratories. This process may have locked the fundamental constants into their current values, like a setting hardening as the universe cooled. But what if that freezing was not perfectly complete? Some of our most ambitious theories, including grand unified theories and models of quantum gravity, suggest that this process could have left behind subtle defects, like tiny cracks in the cosmic ice. These models allow for the possibility that the constants are not absolutely fixed, but are dynamic fields that could have continued to shift, albeit imperceptibly, over billions of years. The expansion of space, therefore, is not merely a backdrop. It is an active, changing environment, a stage that has been stretching and cooling since the beginning of time. And if the stage is changing, we must seriously ask if the script, the fundamental laws written into its fabric, have been subtly edited across the eons. This profound question leads us directly to a specific and ancient form of light, a messenger from the distant past that holds the key to this mystery. That faint starlight from a quasar is our most powerful tool for interrogating the ancient universe. These brilliant beacons are the cores of incredibly distant galaxies, powered by supermassive black holes feasting on surrounding matter. Their light can be older than the Earth itself, traveling across cosmic voids for billions of years before finally entering our telescopes. But we are not just looking at the quasars, we are studying what happens to their light on its epic journey to us. As this light traverses the vast emptiness, it passes through immense, diffuse clouds of primordial gas. These clouds are not empty, they are filled with elements like hydrogen, magnesium, and iron. And just like a specific chemical will only absorb certain colors of light in a laboratory experiment, these interstellar atoms absorb very specific wavelengths from the quasar's brilliant beam. The result is a barcode imprinted on the light, a pattern of dark lines called an absorption spectrum. Each line is a direct signature of a specific atom and a specific electron transition within that atom. The precise position of these lines in the spectrum is not arbitrary. It is exquisitely sensitive to the value of a number we call the fine structure constant, represented by the Greek letter alpha. This constant, alpha, governs the strength of the electromagnetic force. It controls how tightly electrons are bound to an atomic nucleus. If the value of alpha were different, even by a minuscule amount, the energy required for these electron jumps would shift. The entire atomic barcode would be minutely stretched or compressed. This gives us a direct test. We can measure the absorption lines from these ancient gas clouds in the quasar light and compare them to the exact same lines produced by those atoms in our laboratories today. If the patterns do not match perfectly, if the lines are systematically shifted in a way that cannot be explained by the expansion of the universe alone, it would be direct evidence that the laws of electromagnetism were different when that light began its journey. In the late 1990s, a team led by astronomer John Webb began this painstaking work. Using the most powerful telescopes on Earth, they collected the faint light from dozens of quasars. They analyzed thousands of these ancient absorption lines, hunting for any subtle drift in the cosmic barcode. Their initial findings were astonishing. The data seemed to suggest that billions of years ago, the fine structure constant, alpha, was very slightly smaller than it is today. The electromagnetic force may have been a tiny bit weaker in the distant past. The implications of such a discovery were profound, sending a tremor through the world of fundamental physics. It suggested that the universe's operating system might have received a minor update over cosmic time. This technique of using quasar spectra transforms the entire observable cosmos into a grand, natural laboratory, one that allows us to run an experiment across billions of years. But a single extraordinary claim requires extraordinary evidence, and the scientific method demands that we seek confirmation from other, completely independent cosmic clocks. While astronomers were looking to the skies, Earth itself provided a second, more intimate laboratory. Deep underground in Gabon, Africa, lies the site of an ancient and entirely natural nuclear reactor. 2 billion years ago, in a rich vein of uranium ore, the precise conditions aligned for a self-sustaining fission reaction to begin. For hundreds of thousands of years, this natural reactor, now known as Oklo, hummed with nuclear activity, all without a single human engineer. It was a perfect prehistoric experiment, and the radioactive waste it left behind became a time capsule. The nuclear chain reactions that powered Oklo are not random. They depend on a delicate nuclear ballet, one that is incredibly sensitive to the exact strengths of the fundamental forces. In particular, a specific isotope of a rare earth element called samarium acts as a nuclear sponge, absorbing neutrons to keep the reaction under control. How well that samarium soaks up neutrons depends directly on the value of the fine structure constant, the same alpha we encountered in the quasar light. If alpha had been even slightly different 2 billion years ago, the samarium would have absorbed neutrons either too efficiently or not efficiently enough. The reactor would have either fizzled out immediately or run wildly out of control, leaving a very different radioactive signature in the ore. Scientists have painstakingly analyzed the fossilized nuclear waste at Oklo, measuring the precise ratios of the elements left behind. The results are staggeringly precise. They show that for the reactor to have functioned exactly as it did, the fine structure constant could not have changed by more than a tiny fraction of 1% over the last 2 billion years. This is an incredibly tight constraint, a verdict delivered by the Earth itself. Here, then, is a direct conflict. The ancient quasar light seems to whisper of a changing constant, while the terrestrial rocks of Oklo proclaim a story of profound stability. This is not a failure of science, it is the very engine of discovery. A scientific mystery is at its most compelling when two impeccable lines of evidence point in opposite directions. One group of scientists is looking out across the cosmos, while another is looking down into the ground, and they are seeing two different versions of history. So who is right? Could there be an error in the quasar data, a subtle systematic effect we have not yet accounted for, or is the truth even stranger? Perhaps the constants do vary, but not uniformly throughout space. The universe might be a patchwork, with the rules of physics subtly different in one cosmic neighborhood compared to another. Our search for a simple answer has instead opened a door to a far more complex and fascinating reality. So we are left with two conflicting stories from the past, but what about the present moment? The ticking of a clock is one of the most fundamental rhythms of our reality, and we now possess clocks of such breathtaking precision that they can test the constancy of the laws of physics in real time. These are atomic clocks, the ultimate timekeepers of the modern era. They do not rely on swinging pendulums or vibrating quartz crystals. Instead, they measure time by counting the oscillations of atoms themselves. An atom of cesium, for instance, has a specific hyperfine transition between energy levels, and it will resonate at that exact frequency over 9 billion times per second with unerring regularity. This natural vibration is so stable that the best atomic clocks would not gain or lose a single second over the entire age of the universe. The key to this phenomenal accuracy is that the ticking rate of these atomic clocks is locked to the value of the fine structure constant. That same number, alpha, which we encountered in the ancient quasar light and the Oklo reactor, directly controls the energy levels within an atom and therefore the frequency at which it ticks. Scientists have devised an ingenious experiment using this principle. They build different types of atomic clocks, perhaps one based on the microwave frequency of cesium atoms and another based on the optical frequency of a trapped strontium ion. These two clocks tick at vastly different rates, but their relative speeds are governed by the precise, unchanging values of the fundamental constants. Now, imagine running these two incredibly precise clocks side by side for years, even decades. If the fine structure constant were slowly drifting, even by an infinitesimal amount, the relationship between the microwave and optical transitions would change. One type of clock would very gradually begin to tick faster or slower relative to the other. They would fall out of sync, revealing a fundamental shift in the fabric of reality. Laboratories around the world have performed exactly this experiment. They have networks of these exquisite timepieces, constantly comparing their rhythms. The results are a profound testament to stability. After years of the most sensitive monitoring possible, the clocks remain in perfect lockstep. There is no detectable drift. This tells us that here and now, in our local region of space and time, the fundamental constants are not changing. Any variation must be smaller than 1 part in a billion billion. This incredible null result provides a powerful snapshot of constancy in our present-day universe. It resolves the immediate worry that the rules of physics might be shifting under our feet. Yet, it does not necessarily contradict the quasar data. It simply tells us that if change is happening, it is either too slow to be measured over a human lifetime, or it was a phenomenon of the deep past that has since settled down. Our search for a definitive answer now pushes us to look at the very oldest light in existence, the afterglow of the Big Bang itself. This faint afterglow is the oldest light we can ever hope to see, a direct echo from the universe's first infancy. It is called the cosmic microwave background, a whisper of heat that fills every corner of the sky. This glow is a snapshot of the cosmos when it was just 380,000 years old, a moment when it cooled enough for the first stable atoms to form and for light to finally travel freely across space. But this relic radiation is not perfectly smooth. It is imprinted with a pattern of incredibly subtle temperature variations, hotter and colder spots that are a frozen record of the density fluctuations in the primordial universe. These tiny ripples are a cosmic goldmine, and their precise statistical pattern, what scientists call the power spectrum, holds encoded within it the values of the fundamental constants from that foundational era. Think of these patterns as the universe's own fingerprint. The specific spacing and relative heights of the peaks in this spectrum depend critically on the physics of the early universe. For example, the fine structure constant, alpha, governed how tightly protons and electrons combined to form those first atoms, a process known as recombination. The speed of this process directly influenced how those primordial sound waves, the acoustic oscillations, froze into the sky we see today. Similarly, the mass of the electron played a crucial role in how matter and radiation interacted. If either of these values were even slightly different in that ancient epoch, the cosmic fingerprint would be measurably altered. The peaks in the power spectrum would be in different places or have different relative amplitudes. Missions like the Planck Space Observatory have mapped this fossilized light with breathtaking precision, creating the most detailed baby picture of the universe ever produced. Cosmologists then run countless computer simulations, comparing the actual Planck data against models where the fundamental constants are allowed to vary. So far, the data is remarkably consistent with no change at all. The constants we measure in our labs today appear to have been in effect when the universe was a mere 380,000 years old. This null result from the dawn of time provides a powerful, independent check. It tells us that for at least the last 13.8 billion years, the bedrock rules have been incredibly stable. Yet the search is far from over. The precision of these measurements is constantly improving, and even this consistency places incredibly tight constraints on how much any constant could have drifted. A confirmed variation in the cosmic microwave background would be a discovery of monumental proportions. It would mean the laws of physics themselves were literally different in the ancient cosmos, that the infant universe operated under a slightly different set of rules than the mature one we inhabit today. This concept of a cosmos where the very laws are in flux forces us to confront the most profound theoretical frameworks ever conceived by the human mind. What kind of universe allows its own operating code to be rewritten, and what does that tell us about the ultimate nature of reality itself? Our most trusted theories of physics offer no room for changing constants. The Standard Model, our blueprint for particles and forces, and Einstein's general relativity, our theory of gravity, are both built upon the assumption that these numbers are truly fixed. For constants to vary, our current understanding must be incomplete, a compelling approximation of a deeper, more dynamic truth. So what kind of universe allows its rules to be rewritten? The answer may lie in the concept of scalar fields. Imagine an invisible energy field that fills every cubic inch of the cosmos, a background hum of reality. You are already familiar with one such field, the Higgs field, which gives particles their mass. But theoretical physics suggests there could be others, fields whose energy value is not constant. These scalar fields can slowly roll or shift their value across cosmic time, like a vast, invisible ocean settling into a new equilibrium. Now, suppose one of these fundamental constants, like the fine structure constant, is not a number at all, but is actually tied to the value of such a field. As the field evolves, the constant it controls evolves with it. The number we measure in our experiments would then be a local reading, a temporary value in a grand cosmic story. This idea is not just speculative, it is a feature of our most ambitious attempts to unify physics. String theory, for instance, proposes that the fundamental ingredients of reality are not point particles, but incredibly tiny, vibrating strings. The properties of these vibrations determine the particles and forces we observe. Crucially, string theory requires extra dimensions of space, dimensions curled up into shapes far smaller than an atom. The geometry of these hidden dimensions, their size and shape, directly determines the values of the constants we measure in our four-dimensional world. The speed of light, the strength of gravity, the mass of the electron, all could be locked to the shape of this unseen geometry. And if that geometry can evolve, if the hidden dimensions can shift and reconfigure over billions of years, then the laws of physics themselves would slowly transform. This transforms our entire perspective. The constants are no longer immutable inputs written into the universe's source code. They become dynamic outputs, the evolving consequences of a deeper, hidden reality. They are more like the temperature of the universe, a value that was different in the past and will be different in the future, rather than an abstract, eternal number. This profound shift turns a philosophical puzzle into a tangible physical question. We are no longer just asking if the constants change, we are asking how the underlying fabric of the cosmos is evolving. Every new observation, from the light of distant quasars to the ticking of atomic clocks, becomes a potential window into the geometry of hidden dimensions and the role of invisible fields. The search for varying constants is no longer a fringe inquiry. It is a direct pathway to the ultimate theory of everything. The idea of a single, static set of physical laws gives way to a vista of staggering possibility within the framework of string theory. This ambitious attempt to unify all forces and particles suggests that the fundamental constants we measure are not the only possible values. They are merely the ones that happen to exist in our particular cosmic neighborhood. String theory paints a picture of a multiverse, a vast landscape of potential realities, each with its own unique combination of physical laws. In this grand panorama, our universe is not special or inevitable. It is simply one possibility that was randomly selected, likely during the frantic expansion of cosmic inflation. The speed of light, the strength of gravity, and the mass of the electron are not written into the universe's core programming. They are more like the local climate of a single planet in an infinite galaxy, a temporary and contingent set of conditions. This perspective is both humbling and unsettling. It suggests that the precise tuning of the constants that allows for our existence was not a designed outcome, but a cosmic accident. We are living in one of the rare pockets of the multiverse where the numbers just happen to be right for stars, planets, and life to emerge. But the implications grow even more profound when we consider the stability of this local environment. The vacuum of space is not truly empty, it is seething with quantum energy. According to this landscape idea, the state of our vacuum, which dictates the values of our constants, might not be perfectly stable. It could be a false vacuum, a temporary valley in the energy landscape of reality. Over timescales so vast they defy comprehension, a quantum fluctuation could trigger a catastrophic decay. A bubble of a new, more stable vacuum could spontaneously form and begin expanding at nearly the speed of light. Within this bubble, the laws of physics would be completely different. The fine structure constant, the gravitational constant, every fundamental parameter would be rewritten in an instant. This would not be a gentle, gradual drift. It would be a cosmic phase transition, an unstoppable wave of new physics obliterating the old reality in its path. There would be no warning, and the transition would be utterly lethal to any structure, from galaxies to atoms, that depended on the old set of rules. While this scenario is highly speculative and operates on timescales beyond human imagination, its theoretical possibility carries a profound message. The search for varying constants is not merely an academic exercise in measuring tiny decimal places. It is an investigation into the ultimate fragility of reality itself. It forces us to ask whether the stage upon which we live is permanent, or if it is merely a temporary set, waiting in the quiet darkness for its cue to change. This multiverse perspective, born from our most advanced physics, must now face the ultimate judge, the relentless and unforgiving data from our telescopes. The controversy surrounding the varying fine structure constant is a perfect storm of cosmic data and human uncertainty. John Webb's initial findings, which pointed to a smaller alpha in the ancient universe, were based on meticulous observations from the Keck Observatory. But science demands that no single result, no matter how tantalizing, is accepted without intense scrutiny. When other astronomers turned the powerful eyes of the Very Large Telescope in Chile toward the same quasars, the story grew more complex. Their data did not simply confirm or deny the initial claim. Instead, it hinted at a bizarre possibility, a dipole variation across the sky. This would mean that alpha might not just be changing in time, but that its value could depend on which direction you look, as if the universe has a preferred axis where the laws of physics are subtly different. Such a notion is even more radical than a simple, uniform drift. critics of the original result have raised crucial questions. Could the delicate measurements be skewed by unknown properties within the giant gas clouds themselves? The physics of these distant absorbers is not something we can test in a lab. Perhaps the spectrographs on the telescopes, instruments of immense complexity, have tiny, uncorrected imperfections that mimic the signal of a changing constant. Every step of the analysis, from collecting the faintest photons to interpreting the forest of absorption lines, is a potential source of hidden systematic error. The statistical significance of the result has been a battleground, with teams reanalyzing the same data sets and arriving at different conclusions about the strength of the evidence. This back and forth is not a sign of failure. It is the sound of the scientific process working as it should. Extraordinary claims are put through a wringer of doubt and verification. The entire debate highlights just how difficult it is to measure a potential shift of 1 part in 100,000 across billions of light years. Resolving this stalemate requires a new generation of tools. Extremely large telescopes with mirrors spanning 30 to 40 meters are being built to gather vastly more light and provide cleaner, more definitive spectra. New, ultra-stable spectrographs are being designed specifically to hunt for these minute variations, instruments that could finally silence the doubts about systematic errors. The quest has also expanded beyond the fine structure constant. Scientists are now applying the same rigorous methods to test the stability of other bedrock numbers, like the proton-to-electron mass ratio. If that number had been different in the past, the vibrations of molecules in those ancient clouds would leave a distinct signature in the quasar light. So far, the evidence for its constancy is strong, but the search continues. This multi-front investigation shows a scientific community relentlessly probing the foundations of reality, willing to follow the data wherever it leads, even if that path is fraught with controversy and uncertainty. While the fine structure constant commands attention, another number operates with equal power behind the scenes of reality. The proton-to-electron mass ratio, often called mu, is a silent giant in the cosmic scheme. Think of a proton as vastly heavier than an electron, outweighing it by about 1,836 times. This specific ratio is not a random figure, it is the anchor for the entire world of chemistry. It dictates how atomic nuclei made of protons and neutrons can hold onto their swarms of much lighter electrons to form stable atoms. If this ratio were significantly larger, electrons would orbit too closely and too quickly, fundamentally warping the chemical bonds that create water, DNA, and every other molecule. If it were smaller, atoms would be puffed up and unstable, unable to form the complex structures necessary for life. This ratio also governs the fierce nuclear fusion that powers stars. A shift in mu would change the energy levels inside atomic nuclei, potentially altering how stars burn their fuel and forge the elements. To test this pillar of stability, astronomers have turned their gaze to the cold molecular clouds drifting between the stars. Within these cosmic nurseries, simple molecules like ammonia perform a delicate dance. An ammonia molecule, shaped like a tiny pyramid, can rotate and vibrate at frequencies exquisitely tuned to the proton-electron mass ratio. Its rotation depends on the masses of the atoms involved, while its internal vibrations are more sensitive to the forces binding them, which are tied to the electron's mass. This creates a unique signature. If mu were different in a distant galaxy, the rotational lines and vibrational lines in the spectrum of ammonia would shift relative to each other and relative to the lines from other molecules. It is like having two different types of clocks in the same room, one that ticks based on the proton's weight and another based on the electrons. If they fall out of sync over cosmic time, we have our evidence. Using incredibly sensitive instruments like the Atacama Large Millimeter Array, ALMA, scientists have compared these molecular clocks in galaxies billions of light-years away. The results so far speak of profound constancy. Any change in the proton-electron mass ratio over the last several billion years is constrained to be less than 1 part in 10 billion. This incredible precision transforms our search from a solitary hunt into a coordinated investigation. We are no longer checking just one dial on the cosmic control panel. We are monitoring several at once. The true power of this multi-constant approach lies in the patterns it could reveal. If only the fine structure constant were found to vary, it might point to a specific mechanism, perhaps the evolution of a single scalar field. But if both alpha and mu were discovered to be drifting in a correlated way, it would be a smoking gun. Such a coordinated shift would point directly to a far more profound upheaval, a fundamental rewriting of physics stemming from a deeper layer of reality, like the slow uncurling of a hidden dimension in string theory. Each constant we test is a separate thread, and by pulling on all of them, we hope to see the entire tapestry of reality move. While the electromagnetic force is tested with atomic clocks and ancient starlight, gravity presents a far more stubborn puzzle. Measuring the strength of gravity, Newton's big G, with high precision is one of the most difficult challenges in all of experimental physics. Unlike other constants, G cannot be measured in a pure quantum system. It requires weighing real, physical masses in a laboratory, where even the subtlest seismic tremor or temperature fluctuation can ruin the result. This fundamental difficulty means our knowledge of G is far less precise than our knowledge of any other constant, making the search for its variation a true test of ingenuity. To overcome this, scientists have turned the solar system itself into their laboratory. For decades, we have been firing laser beams at retroreflector arrays left on the lunar surface by the Apollo astronauts. By timing the light's round trip with exquisite accuracy, the Lunar Laser Ranging Experiment measures the distance between Earth and the Moon down to a matter of centimeters. This creates a continuous, decades-long record of the Moon's orbit. If the gravitational constant G were slowly changing, the subtle tug between Earth and its satellite would shift over time, causing a detectable drift in the lunar orbit that would accumulate in the laser data. After more than 50 years of painstaking measurement, the result is a profound testament to stability. The data shows that G is not changing by more than 1 part in 10 trillion each year. Gravity's pull is as reliable as the tides it helps to create. But what about gravity's behavior across the wider cosmos? For that, we listen to the ticks of nature's most perfect clocks, millisecond pulsars. These are the rapidly spinning, ultra-dense cores of dead stars, beaming out radio pulses with a regularity that rivals our best atomic clocks. When 2 of these pulsars orbit each other, they create a pristine laboratory for testing gravity. A change in G would directly affect the force binding them together, causing their orbital period to speed up or slow down in a specific, predictable way. By monitoring these celestial metronomes for years, astronomers can detect shifts smaller than 1 part in a billion. Once again, the message from the void is one of constancy. Pulsar timing data reveals no evidence that the strength of gravity has changed over these vast interstellar distances. The unwavering nature of G is a foundational pillar of Einstein's general relativity, the theory that describes gravity as the curvature of spacetime itself. Finding a varying G would not be a minor adjustment. It would be a tectonic shift, forcing us to dismantle and rebuild our deepest understanding of how the cosmos is woven together. The very difficulty of these measurements, from bouncing lasers off the Moon to decoding the rhythmic pulses of dead stars, highlights the extraordinary lengths we must go to in order to question the universe's most basic rules. Our universe appears perfectly tailored for life, but this apparent perfection might be the ultimate selection bias. If the fundamental constants are truly variable, then our existence hinges on a cosmic coincidence of staggering improbability. We find ourselves in a universe that allows for stars, planets, and life not because it was designed, but simply because we are here to observe it. This line of reasoning is known as the Anthropic Principle. It confronts the bizarre fine-tuning we see everywhere we look. Consider the strong nuclear force, the glue that binds atomic nuclei together. If this force were just a few % stronger, the universe would be a very different place. In the first frantic moments after the Big Bang, all the hydrogen would have fused into helium almost instantly. A universe without hydrogen is a universe without water, without long-lived stable stars like our Sun, and without the most basic ingredient for the chemistry of life as we know it. Conversely, if the strong force were slightly weaker, it could not overcome the repulsive force between protons. The formation of heavy elements like carbon and oxygen in the hearts of stars would become impossible. There would be no planets, no rocky worlds, just a thin soup of light elements drifting forever in the dark. This is not the only razor's edge. The precise value of the gravitational constant determines how efficiently matter clumps together to form galaxies and stars. If gravity were stronger, the universe might have collapsed back on itself immediately in a big crunch. If it were weaker, matter would never have coalesced, and the cosmos would remain a formless, expanding cloud of gas. We exist within a window of viability so narrow it defies belief. The Anthropic Principle offers a framework for this puzzle, especially within the context of a multiverse. If our cosmos is just one bubble in an infinite froth of universes, each with its own randomly selected set of physical constants, then it is no surprise we find ourselves in one of the rare habitable ones. We could not possibly observe a universe that forbids our existence. This idea is deeply controversial. To its proponents, it is a profound insight that explains the most fundamental fact of our reality, why the numbers are the way they are. To its detractors, it is an untestable cop-out, a philosophical surrender that halts scientific inquiry by saying the universe is the way it is because we are here. It does not explain the origin of the constants or the mechanism that sets their values. What it does provide is a powerful link between the search for varying constants and the ultimate question of our own place in the cosmos. It transforms the laws of physics from inevitable truths into local bylaws, making our existence not a predetermined miracle, but a fortunate accident in a vast and mostly inhospitable meta-reality. The accelerating expansion of the universe has torn a hole in our understanding of physics. We call the culprit dark energy, a mysterious force that seems to be stretching the very fabric of space faster and faster. The simplest explanation for this bizarre phenomenon is Einstein's cosmological constant, a kind of fixed energy woven into the vacuum of space itself. But what if dark energy is not a static feature, but something alive, something dynamic? Many cosmologists now champion an idea called quintessence. Imagine quintessence not as a constant, but as a new kind of field, an invisible fluid that fills the cosmos. Unlike the cosmological constant, this field can shift and evolve over time, its energy density slowly changing as the universe ages. This dynamic nature could explain why dark energy's influence seems to have changed over cosmic history. But here is the profound connection. This quintessence field would not exist in isolation. In the tangled web of fundamental physics, fields talk to each other. A dynamic quintessence field could be subtly coupled to the fields that determine other constants, like the fine structure constant. As the quintessence field rolls and evolves, driving the acceleration of the universe, it could gently tug on the dials of other forces. The strength of electromagnetism, the value of alpha, could be slowly changing in concert with the expansion history of the cosmos. In this breathtaking picture, the two great mysteries, the accelerating universe and the potentially varying constants, become intertwined. They are not separate puzzles, but different symptoms of the same underlying cause, the slow, grand evolution of a new cosmic element. This theoretical link gives us a powerful new way to test these ideas. By carefully mapping the history of the universe's expansion and comparing it to any potential drift in the fundamental constants, we can search for a correlation. If we find that the constants were changing more rapidly during an era when dark energy was also behaving differently, it would be a monumental discovery. It would be the smoking gun for a dynamic dark energy and would forever link the fate of the cosmos to the stability of its own physical laws. Back on Earth, far from the distant quasars and cosmic backgrounds, a different kind of hunt is underway in the silent, controlled environments of advanced laboratories. Here, scientists are constructing the most precise measuring devices ever built, instruments so sensitive they could detect a shift in the fundamental constants occurring over a single human lifetime. These are not telescopes, but intricate networks of lasers, mirrors, and isolated atomic systems, all designed to catch the universe in the act of rewriting its own rules. One powerful technique involves trapping a single atom or a small cloud of them using electromagnetic fields, suspending them in a perfect vacuum where they are almost completely free from external disturbance. Researchers then probe these atoms with lasers of exceptional stability, measuring the exact frequency of light needed to cause an electron to jump between two specific energy levels. This frequency is a direct reflection of the fine structure constant. The true power of this method comes from comparison. By simultaneously monitoring two different types of atomic transitions within the same apparatus, transitions that depend on the fundamental constants in slightly different ways, scientists create a built-in cosmic clock and a cosmic ruler. If the fine structure constant were to drift, the ratio between these two frequencies would change. It is like having two perfectly synchronized watches, one that ticks based on a pendulum and another on a quartz crystal. If the fundamental nature of time itself began to shift, the watches would slowly fall out of sync, revealing the hidden change. The stability required for these experiments is almost beyond comprehension. The lasers are locked to ultra-stable optical cavities, structures made of materials specially chosen to resist expansion and contraction from tiny temperature fluctuations. The entire apparatus is often shielded from the Earth's magnetic field and isolated from seismic vibrations, the gentle hum of our living planet. After years of continuous monitoring, the results are a profound whisper of constancy. Any present-day change in the fine structure constant is smaller than 1 part in a billion per year. This incredible null result from the lab tells a clear story for our local region of space-time. The constants are not actively shifting beneath our feet in a way we can currently measure. These Earth-bound experiments provide a crucial, real-time snapshot that complements the astronomical view. While the quasar data looks for evidence of dramatic shifts over billions of years, the laboratory searches for the faint, steady creep of change in the here and now. That we have found none suggests a cosmos that is remarkably stable in its maturity, even if its youth might have been more dynamic. This relentless pursuit of precision on Earth is not a separate quest, but a vital strand in the same grand investigation, tightening the constraints on reality from our own backyard and forcing the mystery of the distant past to become even more precise. The search for varying constants forces us to confront an even more radical possibility. What if the laws of physics are not the same everywhere? We have been probing the universe's history, looking for changes across time, but the cosmos also stretches across unimaginable distances. Could the fine structure constant have one value here in our galactic neighborhood and a slightly different value in a galaxy on the far side of the observable universe? This idea directly challenges one of the most cherished principles in cosmology, the cosmological principle. This principle states that on the very largest scales, the universe is both homogeneous and isotropic. It looks roughly the same in every direction and the same basic rules apply everywhere. This assumption is the bedrock of modern cosmology, allowing us to use observations from our tiny corner of space to make bold claims about the cosmos as a whole. To test this profound idea, astronomers have returned to the quasar absorption spectra with a new question. Instead of just looking for a change between the past and the present, they are now mapping the data across the sky, searching for a pattern, a directional dependence. Imagine the universe having a preferred axis, a kind of cosmic north. Along this axis, the fine structure constant might be measured as slightly stronger, while in the opposite direction, it appears slightly weaker. This kind of pattern is known as a dipole. Some reanalyses of the existing quasar data have indeed hinted at the existence of such a dipole. The evidence suggests that in one particular direction of the sky, the value of alpha might be larger, while in the opposite direction it is smaller. This is a staggering claim. It implies that the universe has a fundamental lopsidedness to its very laws, a grand asymmetry woven into the fabric of reality. Unsurprisingly, this result remains fiercely debated and highly controversial. Critics argue it could still be a monumental artifact, a systematic error hidden within the immense complexity of the telescopic measurements. Perhaps the distribution of the gas clouds themselves creates an illusion, or some subtle, unaccounted for effect in the spectrographs mimics this signal. The statistical significance is a battleground, and the scientific community is rightly skeptical. Yet, the mere possibility is electrifying. A confirmed spatial variation would be far more revolutionary than a simple change over time. A temporal drift could be seen as the universe maturing, its settings slowly adjusting as it ages, but a spatial variation means there is no single, universal rulebook. The laws of physics would become more like local ordinances, different from one cosmic continent to another. Your address in the cosmos would determine the numerical values that govern reality. This would force a complete rewrite of our cosmological models, shattering the principle of a uniform universe and opening the door to a reality far stranger and more complex than we ever imagined. Resolving this mystery requires a definitive, full sky map of constant values, a project that will drive the science of the coming decades and become a primary goal for the next generation of giant telescopes. The final verdict on our cosmic rulebook will be delivered by a new generation of eyes on the sky. Giants like the extremely large telescope are rising from mountaintops, their 39-meter mirrors poised to catch ancient starlight with a clarity we have never known. This colossal light bucket will do more than just take prettier pictures. It will gather photons from the faintest quasars in such abundance that the noisy, static plaguing current spectra will fade into insignificance. We will see the atomic barcodes imprinted on that light with crystalline sharpness, finally silencing the debate over whether the observed shifts are real or merely instrumental ghosts. At the same time, orbiting high above our atmosphere, the James Webb Space Telescope is already peering into the infrared, a part of the spectrum crucial for observing the most distant, redshifted galaxies. It is analyzing the chemical fingerprints of the very first stars, testing the nuclear reactions that forged the earliest elements. If the constants were different back then, Webb should see the subtle chemical anomalies left behind in these primordial stellar nurseries. And looking ahead, ambitious space missions are being designed with one explicit goal: to map the cosmic microwave background and the large-scale structure of the universe with a precision that seems almost like science fiction. These future observatories will measure the primordial ripples in such exquisite detail that any variation in the constants during the universe's first moments will be laid bare. This is not merely an upgrade in technology, it is a paradigm shift in our quest. We are moving from tentative, controversy-riddled measurements to a robust, multi-pronged experimental assault on the problem. We are building the instruments that will finally tell us if the numbers in our physics textbooks are eternal truths or just a single page from a much longer and far more dynamic cosmic story. A confirmed drift in the fine structure constant would shatter the very architecture of particle physics. Our current understanding, the incredibly successful Standard Model, is a tightly woven tapestry where every thread is precisely connected. The fine structure constant, alpha, is not a free-floating number in this model. It is a composite, a value derived from a very specific relationship between three other pillars: the elementary charge of the electron, Planck's constant from the quantum world, and the cosmic speed limit, the speed of light. Think of it like a recipe where the final flavor depends on the exact amounts of salt, flour, and water. If the final taste, alpha, is changing, then at least one of those core ingredients must be changing with it. This simple realization has explosive consequences. It means that at least one of these quantities we considered an immutable bedrock of reality is not bedrock at all. It is shifting sand. Such a discovery would force a radical rewrite of quantum electrodynamics, our most precise theory of how light and matter interact. The entire mathematical elegance of the Standard Model, with its perfectly calibrated relationships, would be broken. The equations that have predicted the outcomes of every experiment at the Large Hadron Collider would be fundamentally incomplete. For physicists, this is not a failure but a revolution. A varying constant would be the clearest possible signal of physics beyond the Standard Model. It would be direct experimental evidence that our current theory is just an approximation, a low-energy shadow of a much deeper and more dynamic reality. This single astronomical observation could provide clues that are completely inaccessible to even the most powerful particle colliders on Earth. Colliders smash matter together to see what emerges, but they operate under the assumption that the rules of the game are fixed. They cannot test if the rules themselves are evolving. A changing alpha would be like discovering that the game of chess is being played with pieces that slowly transform their moves over centuries. It would point unequivocally towards the grand unified theories and string models that attempt to describe the universe at its most fundamental level, where the constants are not numbers but the dynamic outcomes of hidden fields and curled-up dimensions. This transforms the entire quest from a measurement of tiny decimal points into a direct line of inquiry into the heart of reality. This unsettling possibility strikes at the very heart of what we consider real. For centuries, we have believed that the laws of physics are like eternal mathematical truths, existing on a plane beyond the universe they govern. They were the timeless, transcendent rules that the cosmos simply had to obey. But if the constants can change, that entire framework collapses. The laws are no longer the unchanging directors of the cosmic play. They become part of the performance itself. They are not the stage, but actors moving and evolving with the plot. This implies that what we call the laws of physics are not fundamental at all. They emerge from something deeper, a dynamical substrate whose nature we can only guess at. We are forced to shift our entire perspective from a universe that simply is to a universe that actively becomes. This is a profound transition. It challenges our deepest notions of eternal truth within science. The beautiful, immutable equations we have discovered may not be universal truths, but merely a local description, a snapshot of the rules as they happen to be in our corner of space and time. The line between the laws themselves and the momentary state of the universe becomes blurred. The constants become less like fixed parameters and more like evolving properties of the cosmic environment, akin to its temperature or density. This fluid reality carries a stunning implication for our own existence. The apparent fine-tuning of the universe for life might not be a one-in-a-billion miracle. Instead, in a cosmos where the rules themselves can evolve, the emergence of complexity and life could be a natural potential, an outcome that becomes possible as the universe matures and its laws settle into a habitable niche. We are not the beneficiaries of a single, incredibly lucky roll of the dice. We are the products of a cosmic landscape rich with possibility and change. This perspective is deeply humbling, reminding us that our most cherished physical laws might be provincial bylaws, yet it is also strangely empowering. It suggests a cosmos that is not static and predetermined, but one that is creative, exploratory, and perhaps even fertile. The search for varying constants, then, is more than a technical pursuit. It is a philosophical journey that forces us to see physics not as a completed cathedral of knowledge, but as a living, evolving inquiry into a reality that may be far more fluid and wondrous than we ever dared to believe. The greatest obstacle in this quest is not the vastness of space, but the devilish details hidden within our own measurements. We call these systematic errors, the subtle, unaccounted for factors that can perfectly mimic the signal we are desperately trying to find. In the Quasar method, the light we analyze passes through immense clouds of gas whose true physical conditions remain a mystery to us. What if these ancient clouds are subtly different from anything we can create in a lab? They could be slightly hotter, or under a strange internal pressure, or permeated by unknown magnetic fields. Any of these factors could shift the atomic absorption lines in a way that looks exactly like a change in the fine structure constant. The signal we chase is a shift of 1 part in 100,000, a whisper so faint that 1,000 other cosmic whispers could easily drown it out. The telescopes themselves are another source of potential illusion. The spectrographs that dissect the quasar light into its component colors are miracles of engineering, but they are not perfect. A tiny, undetected miscalibration in the instrument, a shift in its optics over years of operation, could imprint a false signal onto the data that looks for all the world like a changing constant. This is not a matter of simple mistakes, but of chasing a phantom at the very limit of our technological capabilities. Even the ancient Oklo reactor presents its own unique challenge. To interpret its fossilized nuclear waste, we must be certain that our understanding of nuclear physics 2 billion years ago is absolutely complete. We have to assume that no unknown nuclear resonances or subtle quantum effects, now lost to deep time, played a role in how that reactor burned. If our models of 2-billion-year-old fission are even slightly incomplete, then our conclusion about the constancy of the fine structure constant could be built on sand. Back in the laboratory, the battle against systematic error reaches an almost absurd level of precision. To detect a potential drift in a constant over a single year, scientists must control for environmental factors that are normally imperceptible. The gentle warmth of a human body standing too close to the apparatus, the faint hum of the Earth's magnetic field, the distant rumble of a truck on a highway, even the microscopic expansion and contraction of the experimental table as the air conditioning cycles on and off, all of these can swamp the infinitesimal signal we seek. This is why the most sensitive lab experiments are housed in isolated, temperature-controlled bunkers, shielded from every conceivable external influence. The claimed signals for variation always exist at the very edge of what our instruments can perceive. This is the territory where systematic effects reign, where the line between a groundbreaking discovery and a monumental artifact becomes dangerously blurred. The scientific process, in response, is a relentless, unglamorous hunt for these hidden errors. Competing teams of researchers will tear apart each other's methodologies, searching for any overlooked flaw. They will reanalyze the same raw data with different statistical techniques, build new instruments to cross-check the results, and propose every possible alternative explanation for the observed signal. This intense scrutiny is not a sign of hostility, but the very essence of how science builds reliable knowledge. It ensures that if a discovery is finally announced, it will not be a fleeting phantom in the data, but a truth built on a foundation of ironclad evidence that has survived the most brutal interrogation imaginable. A single drifting constant could be a fascinating anomaly, but a coordinated shift in multiple constants would be a revolution. The real game changer would not be one dial turning on its own, but several moving together in a precise, locked rhythm. Many of our most ambitious theories, like grand unified theories, predict exactly this kind of correlation. These frameworks propose that the fundamental forces we see as separate today, the strong nuclear force and electromagnetism, were once a single, unified interaction in the universe's fiery youth. If this underlying unity is real, then the constants governing these forces should not be able to change independently. A shift in the fine structure constant, alpha, would demand a proportional, calculated shift in the constant governing the strong force, which in turn influences the proton-to-electron mass ratio, mu. It would be like two gears in a cosmic clockwork, designed to turn in perfect sync. The specific ratio of their change would be a unique fingerprint, a smoking gun pointing directly to the mathematical structure of that hidden, unified law. Astronomers are now elevating the search to this new level of sophistication. Instead of just analyzing atomic absorption lines from distant gas clouds to measure alpha, they are simultaneously scrutinizing the molecular lines from those same clouds to measure mu. They are looking at the same ancient patch of sky with two different lenses, searching for a coordinated whisper in the data. This is a vastly more complex analysis, a delicate symphony of spectral lines where every note must be perfectly understood. But the potential payoff is immeasurable. A correlated signal would be incredibly difficult to dismiss as a mere instrumental fluke or an unlucky statistical fluctuation. Two independent measurements from atoms and molecules telling the same bizarre story about a changing reality would be nearly impossible to ignore. This transforms the entire investigation. We are no longer simply asking if the universe's settings are static. We are beginning to ask how they might be changing and what the specific pattern of that change can teach us. The search for varying constants is maturing from a question of existence into a quest for understanding, a direct line of inquiry into the deepest architecture of physical law. After this immense cosmic investigation, we might find ourselves facing a deeply ironic outcome. What if the final answer, after centuries of questioning and decades of meticulous searching, is that the constants do not change at all? This so-called null result would be far from a failure. It would be one of the most definitive and profound discoveries in the history of science. A confirmation of absolute constancy would act like a cosmic filter, sifting through the countless theoretical models that physicists have imagined. Many popular versions of string theory, along with various quintessence fields and other dynamic proposals that require or predict large variations, would be decisively ruled out. The universe would be telling us that its deepest rules are not just locally stable, but universally and eternally fixed. This would elevate our current theories, the Standard Model and general relativity, to a new level of significance. Their incredible predictive power would be shown to rest on a foundation of absolute rigidity, a bedrock that does not shift across billions of years or billions of light years. The mysterious, seemingly fine-tuned values of the constants would become an even more profound puzzle. If they cannot change, then why do they have the exact values that allow for stars, planets, and life? This line of reasoning could powerfully strengthen the anthropic argument, suggesting that we can only observe a universe whose fixed numbers permit our existence. The question why these numbers would move from the fringes of physics to its very center, a fundamental mystery demanding an explanation. This unwavering stability is itself a feature that cries out for understanding. Why is reality so stubbornly consistent? The search for varying constants is ultimately a win-win endeavor for science. Whether we discover a subtle drift confirming a dynamic, living cosmos, or we confirm an ironclad constancy, we learn something equally profound about the nature of our universe. The journey itself, with all its controversy and dead ends, forces us to question our most basic assumptions and sharpens our tools for probing reality. The final verdict, whatever it may be, will reveal a truth about the cosmic stage upon which we find ourselves. This frontier of physics is often misunderstood, twisted into something it is not. When people hear that the laws of nature might not be constant, a common reaction is to imagine a universe where anything can happen, where the rules of reality are so flexible they might as well be magic. This could not be further from the scientific truth. The search for varying constants is not a free-for-all. It is a precise hunt for minuscule, specific shifts predicted by rigorous mathematical theories. We are not talking about the speed of light suddenly having tomorrow or gravity switching off. In the models physicists take seriously, any change would be glacially slow, unfolding over billions of years. A constant might drift by less than 1 part in a billion over a human lifetime, a change so imperceptible it would have no effect on your daily life, on the stability of our sun, or on the chemical bonds that hold you together. The world would not instantly unravel. It is a change measured in the faintest whispers across cosmic time, not a sudden shout that shatters reality. Another critical point is that this research does not tear down the physics we already know. Newton's laws of motion still perfectly predict the path of a spacecraft. Quantum mechanics still powers the semiconductors in your phone. These theories are not wrong. They are incredibly successful within their domains. The search for varying constants is about finding the outer edges of that success, the point where our current understanding meets something deeper. It is the quest for the ultimate foundation, the fundamental theory that explains why our current rules work so well in the first place. Clear communication is the bridge between this complex science and public wonder. By separating the careful, evidence-based investigation from sensational speculation, we can share the genuine excitement of this search without venturing into pseudoscience. The real story of a cosmos whose deepest laws might have a history of their own is astonishing enough. This grand cosmic investigation is not reserved for a small elite with access to giant observatories. The search for the universe's deepest secrets has a place for anyone with a passion for the night sky. Amateur astronomers, equipped with increasingly sophisticated backyard telescopes, are contributing in a vital way by monitoring the behavior of specific celestial objects. They keep a watchful eye on certain types of variable stars and the brilliant cores of active galaxies, tracking their subtle changes in brightness over months and years. This consistent, long-term data collection creates a precious historical record, a baseline of stellar behavior that professional astronomers simply do not have the telescope time to maintain. A single, unexpected flicker in a galaxy monitored for a decade by a dedicated amateur could provide a crucial clue. Beyond the telescope itself, there is another frontier where everyone can participate, the vast ocean of data that has already been collected. Citizen science projects harness the incredible power of human intuition and pattern recognition. Classifying the intricate spectra of thousands of quasars or scanning enormous datasets for rare anomalies are tasks where the human brain still outperforms even the most advanced algorithms. Platforms like Zooniverse have proven that when thousands of curious minds work together, they can achieve what would take a small research team a lifetime. This collaborative effort does more than just crunch numbers. It builds a bridge between the public and the profound questions at the edge of our knowledge. By taking part, people gain a first-hand understanding of the scientific process, with all its careful scrutiny and thrilling uncertainty. The quest to understand the constancy of the cosmos is fundamentally a human story, and inviting wider participation ensures that this grandest of all mysteries remains a shared endeavor for all of us. This quest to test the universe's stability is a tapestry woven from many scientific threads. It reveals a stunning collaboration between fields that, on the surface, seem worlds apart. High-energy particle physics provides the theoretical framework, offering the why by showing how a changing constant would shatter our current models and point toward a deeper reality. Cosmology provides the grand stage and the historical data, using ancient starlight and the cosmic microwave background as its evidence. But these grand questions demand more than just theories and distant observations. They require measurements of almost impossible precision. This is where atomic physics and metrology, the science of measurement itself, enter the story. In quiet laboratories, scientists have developed clocks so precise they would not lose a second over the entire age of the universe. These are not just timekeepers, they are exquisitely tuned instruments designed to detect the faintest whisper of a drifting constant in real time. The entire endeavor is a perfect example of cross-pollination. The relentless drive to answer a fundamental cosmic question forces us to invent better tools. The ultra-stable lasers and vibration-isolated optical cavities created for these constant hunting experiments do not stay locked in a lab. They find other lives. The same precision technology directly improves the accuracy of the global positioning system, making your phone's map more reliable. It refines international timekeeping standards and even enhances our ability to detect the faint ripples of gravitational waves from colliding black holes. This is the hidden engine of fundamental research. A question about the immutable nature of physical law does not exist in an ivory tower. It echoes through engineering and practical innovation, proving that our deepest curiosity about the cosmos often builds the very technologies that reshape our world. The search for varying constants is more than a single experiment. It is a unifying mission that brings together cosmologists, particle theorists, atomic clock engineers, and metrologists, all speaking a common language of precision in their shared pursuit of one of reality's ultimate secrets. The journey to test the universe's stability has its own history, a timeline marked by radical ideas and relentless experiments. In 1937, Paul Dirac first challenged the static view with his large number hypothesis, suggesting gravity itself might weaken over time. For decades, the idea remained a theoretical curiosity until 1961, when Karl Brands and Robert Dicke provided a serious mathematical framework. Their scalar tensor theory of gravity formally allowed the gravitational constant to vary, transforming a philosophical puzzle into a tangible physical question. The concept then lay mostly dormant, awaiting the tools to test it. The breakthrough arrived at the turn of the millennium. In 1999, astronomer John Webb and his team analyzed ancient quasar light from the Keck Observatory and announced a staggering finding. Their data suggested the fine structure constant was slightly weaker billions of years ago. The physics community was electrified and deeply skeptical in equal measure. Just 5 years later, a completely different kind of evidence emerged from the depths of the Earth. The analysis of the 2-billion-year-old Oklo natural nuclear reactor placed an incredibly tight constraint, arguing for a constant that had not budged. The two lines of evidence were in direct conflict, one from the distant cosmos and one from our own planet, and the debate was ignited. The 21st century saw the battle of precision intensify. By 2010, laboratory atomic clock comparisons, the most sensitive local tests ever devised, confirmed that any present-day drift was undetectably small. But then, in 2011, the controversy took an even stranger turn. A reanalysis of the quasar data claimed the variation was not in time, but in space, suggesting a cosmic dipole where the laws of physics were lopsided. This was a claim so radical it was met with fierce scrutiny. Throughout the 2020s, powerful new telescopes like the Very Large Telescope and the Atacama Large Millimeter Array have delivered ever more precise data, sometimes conflicting, but always tightening the noose around the possibility of variation. The field today is not defined by a single answer, but by a vibrant and healthy controversy. It is a process of bold claims meeting rigorous criticism, a cycle that has propelled a speculative hypothesis into a major experimental frontier. The next chapter in this timeline is not a distant possibility. It is being written right now in the control rooms of new observatories, where the next generation of giants is preparing to deliver a verdict. This search for a shifting reality stands as one of science's most profound journeys. We have traveled from the theoretical spark of Dirac's numbers to the silent ticking of atomic clocks, from the ancient whispers of quasar light to the fossilized snapshot of the Big Bang's afterglow. The evidence we have gathered paints a complex and contradictory portrait, a cosmic tug-of-war between tantalizing hints of change and powerful declarations of stability. Yet the ultimate answer, whether the constants drift or stand firm, is almost secondary to the quest itself. This relentless investigation has already reshaped our understanding, pushing the boundaries of technology and forcing us to ask deeper questions about the very nature of existence and the laws we once thought were eternal. The possibility of an inconstant cosmos opens a breathtaking window into a universe that is not a static monument, but a living, evolving, and deeply creative arena. As we stand on the brink of new discoveries with colossal telescopes and ever more precise instruments coming online, we are reminded that the universe is not yet finished revealing its secrets. The final chapter on the constancy of physical law remains unwritten, its pages waiting to be filled by the observations of the next generation. We invite you to stay curious, to follow these unfolding discoveries, and to share your own thoughts on this mind-bending frontier in the comments